and I'm happy to be back. Thank you very much for the organizing committee for inviting me a second time for giving the presentation. Today's topic is about building tomorrow and how AI transforms the structural engineering. And there is a lot that we see nowadays, so I'll try through this presentation to de-clarify, de-qualify a lot of things that are happening. So I'm going to start my presentation with what I started showing in last year's event in IAS, when I was talking about modular and prefab buildings. And one of the key messages was that despite the fact that we're talking about highly standardized and customized structures, the outcome of every construction project nowadays is quite unique and it's quite complicated in terms of shape and function. And I've also mentioned about the housing demands and the role of tall buildings in the megacities of the world, and these kind of structures, they're kind of very complicated, multifunctional, and they require advanced engineering skills in order to be designed. So the presentation was ending with the so-called vertical cities and the concept of designing for adaptability, flexibility, design for deconstruction, and design for reuse. And in order to be able to actually design these kind of buildings, the buildings of the future, these kind of smart structures, we will need assistance. We will need help. We cannot just do it with today's tools. So I'm going to start this presentation with a little story. So please bear with me. It's not going to take more than 5-6 minutes. I'm going to read it out. I've written it myself, but I have to read it out. I cannot remember it off my head. And that first title was the official title of the presentation, but the actual title of the presentation is Alex and the AI Adventure. Okay. So try to, while I'm reading that story, to think your work and how your work fits in that kind of story, and what do you think is going to be the future for you, and we'll see how things will be unfolded after the story. So once upon a time, in a city buzzing with live skyscrapers and endless construction cranes, there was a young structural engineer named Alex. She had just landed the biggest project of her career, designing a futuristic, eco-friendly skyscraper right in the heart of the city. The challenge was enormous, but Alex was confident. She had a trustworthy AI system at her sidekick. But this wasn't just any ordinary tool. It was like a super smart assistant with a memory of 1,000 engineers and a patience of a saint. So Alex called the system ARTI, short for Artificial Intelligence and Tech. ARTI didn't perform miracles, but it was sure made things easier when it came to solving engineering headaches. And oh boy, there were many of these. On the first day, Alex was struggling at her screen, feeling the pressure of the looming deadlines. This building needs to be lightweight, eco-friendly, strong enough to survive earthquakes, and wait for it, pretty. Alex said, why can't we just build cubes? Alex thinks outside the box, literally, Arti said, with a cheeky on-screen message. Arti's design tool wasn't just running standard calculations, it was generating ideas based on years of structural engineering data. Alex plugged in her criteria, strength, sustainability, and of course that wow factor that all architects want. Within minutes, Arti presented her with 10 different elegant designs, others weird, others looked like a seashell, a side shell for a skyscraper. Anyway, Alex laughed, but she noticed something. The AI had figured out how to reduce the steel framework by 20%, keeping the structure lightweight and using fewer materials without sacrificing safety. It wasn't magic, it was pure physics and years of data crunching. Earthquakes, anyone? Now, time for the hard part. Making sure that this building didn't crumble like a cookie in an earthquake. The city was in a seismic zone, so Alex knew every calculation had to be airtight. She would normally have to run endless simulations, manually tweaking parameters and testing hundreds of scenarios. But with Arti's help, things went a little differently. Arti had been trained on earthquake data from all over the world. Skyscrapers in Tokyo, bridges in San Francisco, buildings that survived and some that didn't, quakes in Chile. With a few clicks, Alex ran simulations not only for earthquakes, but also for high winds. Suddenly, an alert popped up. Did you know a minor change in the foundation depth could increase seismic resilience by 15%? Alex was surprised. What? Just digging a little deeper could make that much of a difference? Artie explained the logic through the detailed calculations. By slightly increasing the depth and changing the material mix of the foundation, the building would stand much better against potential earthquakes. You're saving so much time, Alex said, scribbling down the changes. No magic was involved, just a lot of AI brain power. Alex raised the material dilemma. Sustainable materials were a big part of the plan, but finding the perfect balance between cost, strength, and eco-friendliness was like trying to solve a puzzle with missing pieces. Normally, Alex would have to research suppliers, check material costs, and manually compare every property. But Artie knew a trick. Alex typed in her requirements and bam. Artie began analyzing data from every supplier in the region, from recycled steel to concrete to fancy new green concrete formulas. Wait, what is bioconcrete? Alex wondered, and it popped up as a suggestion. Turns out it's concrete that can heal its own cracks using bacteria. Using bioconcrete could reduce long-term maintenance costs and even extend the life of the building. She quickly added it to the list of materials to propose. Everything was going smoothly until the construction phase. Alex was no relation to the construction of Romania, because they delayed the construction. Alex was reviewing the project timeline when her phone buzzed. The delivery of essential materials had been delayed by a week. This was a nightmare for any project manager, and Alex could feel the stress creeping in. She logged in and asked Artie, what now? How do I avoid domino effect on the rest of the schedule? Artie processed this setback, cross-referenced it with historical data on similar delays, and he said, I've noticed that teams lose time when they sit idle, waiting for materials. Let's reshuffle the tasks, have the team work on the upper framework now while waiting for the foundation materials. That way, we don't waste time. Alex explained that genius, normally a delay like this would have thrown the entire project off track. By re-optimizing the schedule, Artie helped her avoid unnecessary downtime and kept the project on target. It wasn't magic again, it was just really smart project management. As construction continued, it was time for inspection. But some parts of the building were tricky to reach, especially on the upper floors. And that's when Alex decided to use drones. Yes, drones equipped with AI. She sent them up to inspect the beams, checking for any defects. This is so cool, she said. Alex thought as he watched live footage from the drones flying through the skyscraper like little robotic birds. But just when everything seemed perfect, Artie flagged the potential issue. Alert, a misalignment has been detected on the 31st floor. What? Where? Alex zoomed into the drone footage, and sure enough, the beam was slightly off by a few centimeters. Left unchecked, it would have caused issues later down the line. Alex immediately called the construction crew to correct it. Finally, after months of hard work, Alex stood before the completed skyscraper. It was sustainable, beautiful, and structurally sound. The mayor announced that Alex's skyscraper was named Building of the Year, not just for its design, but for managing to cut CO2 emissions by 50%. The construction was faster, safer, and smarter than ever before. As Alex looked at the gleaming structure, Artie popped up on a message with one of the last cheeky messages. Not bad at all for a team of two, huh? Alex laughed. Not bad at all, Artie, not bad at all. So that's the end of the short story about Artie and Alex. And I hope you feel that this is kind of a utopian story, so it's not right here. We're not really doing that today. But believe me, this is the future. This is what we will be doing in a few days, in a few years from now. Let's look at the lessons learned through that story. So first of all, AI has been used as a tool. So a lot of people can think that AI is there to replace us. No, AI is there to empower us, not replace the human expertise. It's used as a means for creativity because it can think beyond traditional designs. It has been used as data-driven decision-making tool, leveraging AI's data. It has helped with the flexible managing delays in order to make sure that there are no setbacks in the project. It was used as an error detection system to find that problem with a team that was a bit eccentric. And finally, last but not least, it democratizes and decentralizes the power. So think about it. Instead of having a manager, and below the manager you have a few engineers that are just listening to that person, you actually have every engineer being able to do quite a lot. Everyone is at the same level because they have the power of the AI in their hand. So what is AI? Is it another tool? Do we desperately need it? Can we do without it? Or is it something that will help us avoiding tragic mistakes, like what happened earlier this month in Romania? Is AI something new? Well, it's not. Machine learning exists since the 1940s. The Alan Turing paper, the very famous paper of Alan Turing and the subsequent example, the test that he did, it was written in the 1950s. We're talking almost a century ago. Deep learning exists since 1980s, and LLMs, for those who don't know, LLMs, the large language models, is the ones that Tsavdaridis is using. These exist since 1930s. So it's not something new. It has been tested quite a lot. The main difference is the compute power and GPUs that we use nowadays, so we can train much bigger volumes of data and we can get better responses. So in a 2023 IBM survey, we found out that around 40% of the companies, they are actually using AI and another 40% are considering using it. They looked at about generative AI. We'll see what this is in a moment. 38%, again, almost more than one third of the companies, they have already implemented generative AI, and more of them are considering it. And out of all the companies that they were surveyed, 55%, they have adopted AI in some sort of form, either as an automation, as a chatbot, or an assistant. So AI has impacted a lot the industries of today, and this is the main industries that has been impacted. Most importantly, the healthcare, oil and gas, marketing, and the finance industry. What is the construction? It's not there. And this is what we see nowadays. We see the impact of the AI on the construction, and it's for us something new, but it has been there for many years when it comes to other industries. So you're using it a lot. You're using AI, you want it or not, every single day when you open your email, and some of them they go into the junk. There's an AI in the background that is clarifying which emails they are junk, which ones are not. Every single time that you're checking your card into an ATM, there is an AI in the background checking who are you, where are you, and if you check it again in another distance, we'll find out if it's a fraud move or not. When you're using this T9 autocorrection for many years now, more than 10 years in your phone, you're using AI for predicting the word, the next word, the one that you want to write. Every single time that you use Google, you use AI. Every single time that you use the chat box, you use AI. Or when you use this stylus or your finger on your phone to write a letter and that becomes a typed letter, you're using AI. You see, so we trust it already. So let's learn what the levels of AI are and how we use them in our sector. So we have this AI, which is the umbrella term, and we have this robotic programming and search algorithms like Google. This is when we say AI, we need this kind of very general term. But there is a more interesting subset of AI, which is the machine learning, and we use it a lot for anomaly detection in fraud prevention, like the ATMs, predictive analytics in forecasting. As a subset of that, we've got the deep learning that we use for image recognition, speech to text, and it has been used a lot during COVID times for the drug research. Large language models, ChatGPT, they are a subset of deep learning, and in fact, they are a different type of foundational model. And we also call the generative AI. So, AI is a very general term. Anything that can do what human beings can, even better, but only for a very focused task, it's an AI. It's misused a lot of times, so we better not use that term too often. Machine learning is anything that is dependent on the data. What sort of data you have, you're training an algorithm, and then you're creating a pattern, and you're trying to find through that pattern what is the outcome. Very simplistic, very, very simple. We have the deep learning, which is the same thing, but now we're having multi-layers, and it's a multi-objective user optimization that you want to achieve. And in order to do that, you use neurons. And this is where things are becoming a bit interesting. When we talk about black box, we talk about deep learning, because we don't understand how these neurons actually work to a great extent. The LLMs, the foundational models, what GPT is using, and I'm sure you've heard a lot about hallucination and all the problems with ChatGPT, is because it has a limited reasoning capability. Chatbots, that we use quite a lot, it's another LLM version, and I'm sure that you've tried chatbots into, like as an assistant in a website, and sometimes after the second or the third question, it tells you, I cannot tell you anything more, so now you have to connect you with an assistant. The problem is that it has a limited reasoning. All these deep fakes and stuff that they are part of LLMs as well. We have the generative AI, and we'll see some examples later on, that generates new content, and that's the beauty of that. And at the end, we have the AGI, the artificial general intelligence or artificial superintelligence, that is an objective-driven model, and it learns through the world models. So it learns through understanding what's happening out there, right? And this is a different color because this is what we are not using in our sector. So you don't have to be afraid of that, like an AI that is taking over the job. In fact, it looks like this. So the different models, they share characteristics between each other, and it looks a bit more complicated. So the workflow is usually that you've got initial-based data, you're training the base data with some of the data that you've got, then you're testing it. If it's okay, you move on. If it's not okay, there is a new process. If it's okay, you create a machine learning model, you feed new data, and you get a prediction. And there is supervised, unsupervised, and reinforcement learning. And each one has different sort of algorithms that we can use. The idea is that machine learning is simple. When it's very simple, it's less accurate. When it's more complex, it's more accurate. They are all of them very cost and time efficient. And there are a few challenges, most importantly, that we need to test the algorithm for that particular example. And that's why there's a lot of research that is happening nowadays on algorithms, on machine learning algorithms. So we use supervised machine learning for structural design optimization, predictive maintenance and structural health monitoring, unsupervised for damage detection, clustering of components, and anomaly detection in structural performance, and we're using reinforcement machine learning in adaptive structural design optimization, so more advanced optimization, structural response in dynamic environments, and optimizing structural retrofitting because it's got a lot of different properties, so we have to be more efficient and effective. So in the past, we used to have the classic, or nowadays actually, let's say, the classic computational engineering. So the computational engineering, any sort of software that we use out there, and I'm not advertising any of this software, just found these pictures online, is actually a combination of mathematics, computer science, and engineering. Right? And the outcome, what you get out of there, is whatever you see in the middle. What AI-based engineering does is that it adds data into that. So now you are using existing data to improve the design in your software. There are not many software that they have already integrated AI, but it will be coming in the future, as we see nowadays with a lot of plugins and a lot of open APIs. But at the moment, you can do it, you have to do it a bit of manually. So you have to create your machine learning architecture and connect it with your software. For instance, in the top example, we see a machine learning algorithm that helps identifying the residual stresses that we need to input into our FE model, the finite element model. Something that in the past it used to be done based on some theoretical empirical values and a lot of assumptions. But now we can come up with a better true values through the machine learning patterns. So in fact, the process looks like this. We've got the concept, we have to collect the data, and that's one of the big problems. We have to identify what sort of tool, what sort of algorithms we're going to use. We have to clean the data, if it's not clean. Then we have to apply the machine learning algorithm and then deploy it to a software or create our own software. So there is a process now, as opposed to just having a software and clicking a few buttons, getting a result. And that is why we need good engineers. This is why we cannot be replaced entirely by just a machine. So by a relatively recent review study, we found out that there is a fair amount of machine learning applied in structural engineering, and as you can see, there is a lot of that has been used for identifying material strength. So different mixes, different sort of like types of members. A lot of it has been used for actually finding what is the concrete strength. Another one order of the literature review that it was found has been used for understanding the capacity of members for buckling, deflection, etc., especially those that are a bit more complicated, and the structural system is more complicated. And then there is another fair portion of that research that has been used for damage detection, structural health monitoring, and other type of analysis and design. And as you can see, in terms of machine learning algorithms, the spread is quite huge. So you can find a lot of different algorithms that have been applied to different applications. And this is what I said before, it's kind of a challenge because you need to find what is the best algorithm to use for the best application you've got based on the data. So it's not as simple as just taking a machine learning algorithm and applying it. And the vast majority is using neural networks, so part of the deep learning, and these XBoost algorithms that they are usually overperforming over other algorithms. But I'm not going to go into the detail of all of them and what they do. Most importantly is that we're looking at a lot of research is happening on the deep learning, so the second level, the subset of machine learning already. What is the most important is to find the fuel for this AI, which is the data centers. And I would like to highlight, and I'll make a few highlights over the presentation, that it's extremely important to collect data. So you in your companies, when you are using real-life projects, you should find ways, I'm sure most of you already do, to collect the data. And this data, ideally, they should be, after some cleaning and some filtering, available on the publicly, so they can be used for training algorithms. In terms of research, we have a few hubs already of data, and we're using those in order to create the best machine learning models. So we need data because we need to create trustworthy algorithms. I found this slide from a presentation from Liku just a week ago that it gives you an idea of how much data we need. Today's LLMs, so the ones, let's say, that Tsavdaridis is using, have been trained on so much data that for a normal person to read it, let's say we read 250 words per minute, we need 350,000 years. And still, there is limited reasoning, right? They don't overperform, as we saw before. But think the same concept, flip it over. A 4-year-old child has seen so much data that the entire LLM has at this moment. So think about us. I don't think that we have any 4-year-old child in this room. So collectively, think how much data you have in your brain, how much things you have seen. We are collectively much superior than what the LLMs are. The biggest difference is that the LLMs, and of course the AGIs and the ASIs, will be saving that data, where we just see a lot of data unconsciously during the day, and we don't save it. Right? When I step down from this presentation, most of you won't even remember my face. Right? But these algorithms, because they are on servers, they're saving that data. So machine learning tools, how we use them? Simplistically, these are coming from different papers, including some of my papers. So looking at complicated failure modes, such as the thin-walled perforated beams with web openings, when we need to identify failure mechanisms like the web push buckling and the variant mechanism. We are having a number of inputs, then we have a few hidden layers. Usually we use ANN, which is a deep learning, so we're using neurons. 2 or 3 layers of neurons is enough to get a pretty accurate result, and then it identifies what is the failure mode. So then you can feed more data to that machine learning model, and then you can get the prediction. And this is what's happening here. So we fed more data into the model. The paper that you see at the top is actually calculations done by Eurogroup 3. And then the ANN is the green line, and you can see that the spread is much smaller. So the percentage of error is much smaller. It's a better fit, okay, of the data. And usually we also come up with a little software that engineers and usually architects at very early on stage we can use for designing the members more accurately. We've done the same for the lateral torsion buckling, again, of long span, thin wall, perforated beams, again another failure mode that is not well documented in Eurogroup 3, and you can see that Eurogroup 3, the American code, some modified versions of Eurogroup 3, they all come up with predictions that they have errors, whereas the ANN, the deep learning model, the one that we see with the magenta color, the percentage of relative error is much smaller. And we keep producing this kind of online, freely available to the public tools where you can go and you can design your own member. More recently, we managed to gather the largest database of steel concrete composite columns subjected to eccentric actual loading, and we did exactly the same process. It was a bit more complicated because we had more variables. We fit the analysis pretty well to the dataset, and then we created with 3 hidden layers, a very robust neural network model that is predicting very nicely the outcome, the axial capacity. And at the same time, we also managed to do a sensitivity study to find which parameter affects the result. So this kind of analysis, they can be done much more reliably with machine learning and deep learning, in fact. And the same has been done for the moment connection of prefab components. Again, different parameters such as the screw diameter, concrete strength, and thicknesses, they were imported, and then you can get the outcome straight away. And perhaps you can connect that to your design software. More complicated scenarios, when we're talking about modular construction, when we have many different components that may fail, you may have to use more than one algorithms together in order to find out what is the outcome. And the same has been done here with multi-objectives, so trying to find the yield load, yield displacement, ultimate load, output displacement at the same time so that we can find the best solution. And again, the sensitivity study with which parameter affects more of the results. ARUB has been using a lot of machine learning in order to find errors in their simulation models. So errors that will be identified based on previous structures that they have done before. So as long as you have enough data on that, an error can be identified that perhaps this member should not be there. Deep learning applications, more about convolutional neural networks that is dealing with pictures, with images. So then you need a number of layers, so filtering models. So usually you need a big number of images. So 40,000 images have been used in order to identify the crack in the concrete, and a similar project in order to identify, in combination with computer vision, to identify the cracks in the mortars and the bricks. And even more interesting, the crack prediction in bending tests. So while you're loading, to be able to identify where the cracks will take place based on huge databases of similar examples. This is my favorite, steel corrosion prediction through pictures. It has been used quite a lot, but the accuracy was not very good so far. Now, with the new models, things are becoming better. So again, training machine learning models and deep learning models with thousands of pictures on the steel corrosion, where you can actually identify the extent of corrosion, the severity of the corrosion, and the reliability of the prediction as well. So just through pictures, you can find out what is the problem in that structure. Think about it. It's not a non-destructive test. It's even just a picture. Right? So a lot of research has been done recently on digitizing old drawings, and there are a lot of old drawings that we have on a paper. So in order to be able to identify how that structure is made, so training what a shear wall looks like, what a partition wall looks like, a door and a window, and a lot of research and a lot of filtering is happening there, and then the digital version of that model, of that drawing, can be produced. When it comes to multi-objective machine learning examples, this is far more complicated, but again more interesting and sometimes actually more accurate, is when you want to create a framework in order to come up with an optimized design. And the framework is what it plays the most significant role here. So let me go through that example because it's super interesting. So you've got the structural engineer who's inputting the design requirements, so what is the size of the building and all that. And then you have the architectural drawings as well, as drawings. And whatever is happening from the structural engineering goes through an LLM, through prompting, through a lot of writing that is converted to a code. And whatever goes from a drawing from an architect, it goes through GANs and GNS, general adversarial networks and general artificial networks, which are much more advanced and more complicated. And they create a number of parameters that they feed back the method selection. As we said, selecting the appropriate algorithm is extremely important. So the algorithm is selected, is executing the algorithm, and then you come up with an optimized section that is optimizing further the model in terms of topology, pattern, and size. And then it goes back and feeds the method selection again, and the algorithm is executed once again. And that loop process is happening multiple times until you reach your design requirements and a new design of the structure, which can then be parameterized. So that is the beauty, that you can come up with different solutions by just changing the parameters, and all of them, they're optimized in terms of topology, pattern, and size, while meeting the architect's requirements. This is one of the commercial products. These are quite complicated, so most of the researchers, they're actually coming up with commercial products for these, where you can easily play with the parameters, you can come up with a new design optimized, and even more advanced on that, you can select beyond to the already existing requirements if you want to optimize your structure in terms of cost, CO2 emissions, time and delivery, and then another level of optimization is going to happen at the same time, changing the entire structure, the architectural, the structure, the pattern of the structure in order to create a more optimized solution. So there are a lot of these commercial tools that are coming up. This is just from a quick review that I did a few weeks ago, and I'm sure there's more of them are coming. The problem at the moment is that those tools, usually, they are not connected with your current design tools. But in the future, most of them will be because of open APIs. So more and more companies, of these big companies with software, they have open APIs, and they will be connecting with those kind of AI-based tools in order to come up with better solutions. But in everything that I just said, there's an elephant in the room. And that is that whatever we do is on this is based on the data set. So the red dots is the data set. The black line is your prediction model, and the blue line is the true value. So once you go outside the data set, it's a black box. And we need to be aware of that. The uncertainty is even higher because it's a multiplier of what's happening in that space outside. So what is the answer? More data. We need more and more data, and that's why I said before that we need to, with your help as well, to collect data and release data in order to be able to train the algorithms in a more safe way. when we move on from the design and we look at the entire building in a city, then there are far more interesting stuff, right? So we're looking at the construction methodologies, the operation, the refurbishment, material supply, so abundance of data that needs to be created. So the way that we want to look at that is that every building is a digital twin. And then we need to pool a lot of data from different sources into that digital twin and maintain that data in some sort of form so that we can use it for the future generations. So wasting data is not an option. So in fact, there are a lot of challenges when you're looking at the physical and the digital twin and you're trying to connect them. There are challenges related to the industry, and there are challenges related to the data collection, and that the data is not synchronized, it's quite sparse, it's not of good quality. So in order to solve the problem, we need to create, and in fact create that circular economy, we need to have AI-enabled digital twins that are connecting the data from the architectural, engineering, and construction industries to all these AI new tools. So the solution actually is the digital twin that will connect this sort of data. The problem, of course, is data privacy, data storage as well. And we have a lot of tools nowadays to collect data, such as beyond the digital twins, point clouds, material passports that are coming up a lot. I'm sure that we heard about them. Track and tracing systems, even the drones. Anything that we use in order to inspect our structures, we should be using it to collect the data and store the data. Let me go through a final example of a multimodal AI, which is a multi-decision-making criteria, and the example of Efestos Hub. Efestos Hub is a project that we have, and now it's a startup. We have also a stand outside in the exhibition area. And let's see what we are doing. So first of all, we are working in the construction sector. We're focusing more on the steel structures, and we're dealing with reuse, because we believe reuse is one of the best ways to preserve what we have. But there are a lot of issues with the reuse, because we're dealing with old buildings and very limited data, with poor quality of data. The steel variability is dramatic. We have most of the times to recondition the data, repurpose it. The supply and the demand chains just don't exist. And the operations usually are in cities, which means that we have time gaps if we want them delayed. So the whole idea is the stock optimization concept, where you take structural members from one structure that it gets deconstructed, not demolished, and you move those properties to a new sort of structure, right? But in reality, it looks like this, and even more complicated, because everything that takes out is got different lengths, different processional properties, different types of damages, different aging, different dents, corrosion levels, etc. So it becomes a very complicated, very complex project. So what we have been working on is a multimodal AI, called that decision-making tool, that collects data from different sources, such as the designers from different softwares, data from donor buildings, these digital twin models, and public data, whatever we find available online, and then it takes it through a number of different modalities, and it blends all that data to come up with improved decision-making capabilities, comprehensive insights, and ultimately to be able to predict the time availability of the material and the material value in terms of the quality of the product that we're coming up with. And then all that data will be fed back to the designers for the new building. So we are creating a number of tools that they are helping engineers as assistants to solve the reuse problem. Okay, so they don't do it automatically for you, they are helping you to find out the best solution. Currently, we're working with a big project in Luxembourg, in which 49 buildings are going to be deconstructed, and we're collecting a lot of data with different types of corrosion in different types of members. We are also having a digital twin of the model. We take it through a number of AI, such as image classification, with using different AI model architectures, and then we come up with an algorithm that says that this material can be reused, or it has to go for reconditioning, repurposing, cleaning, etc., or it has to go for recycling, which is for us the last option. We don't want to recycle. And the outcomes, as reduced rates, they're given back to structural engineers. From a recent case study, we found out that we can save material cost, around 28% of the material cost, 35% of the carbon emissions, and around 50% of the lead time. So you can be more sustainable with AI. And we keep on doing research on these kind of things, of course, and we're now working on a multidimensional Pareto front optimization tool, which will give us more accurate predictions for the reuse rates and for the capability of the reuse as a whole in different types of structures. So, if you think, actually that's a question, I don't think it's working online, so I won't be able to see the statistics. But if you want to scan that code, it will be a short questionnaire, one question with 4 different answers, if you think that prefab concrete can also be reused. So let's take 5 seconds. If you want to take your phone out and take a picture of that, or scan it, just one question. We will be able to see the statistics. Unfortunately, it wasn't working just here live. But we will also be having that in our desk outside. So if you think prefab concrete is reusable or not, something that we've been asked quite a lot recently is whether we will be also working on prefab concrete in our platform, in our project. So I'm not sure it's going to work here. I don't think it's connected. So let me move on with the presentation. So the main takeaways of, if you haven't taken a picture of that, don't worry, we'll be another one on site. So the main takeaways of today's presentation and Alex's story is that, first of all, we need deep synergies between data and computational science. So data is very important, but they need to be communicated with whatever we're doing out there. We need to recognize the accuracy problems and the data limitations and inaccuracies that we have in terms of data. We have to be aware of any sort of uncertainties in the surrogate, the prediction models, in order to be able to unlock the potential of machine learning and deep learning. And we need to be aware that AI can unlock a significant benefits for sustainability and resilience if it is used appropriately. Now, I know that you all think that this guy here came to tell us a lot about AI and convince us that AI is good. Maybe not. So the consequences of AI is job disruption, as we all have heard, data privacy issues, increased regulation, and environmental concerns, especially within those huge data centers that are going to be produced in the future and already are taking over quite a lot of space. And the risks and the dangers of AI is job losses, human biases, data privacy, deepfakes and misinformation, as we see quite a lot nowadays, especially through the media, automated weapons, a lot of discussion on that, and finally, the superintelligence, like this AGI side that I just mentioned. I highly recommend you to go and read this article from Dario Amodei. He's the CEO and founder of Anthropic, on machines of loving grace, and try to convince yourself what will be the future. Okay. So it's not all good, it's not all bad, there is some interesting arguments there. But I don't believe that AI, personally, will replace what we do. I cannot think of that. AI is more or less something like this. So we will be building complex structures, very interesting structures, smart structures, and we will need to have intelligent assistants. We will need to have what we call agents to help us with coming up with better designs for this democratizing and create sort of like a way that everybody is equal and has the same kind of power on the project. In order to succeed, AI needs economy of data, as I've mentioned many times in this presentation, economy of compute, especially for the capacity to compress and store that data, and economy of capital, a lot of investments. What we need at the same time is great engineers and scientists and people that they can work with the AI assistants, they understand them, multidisciplinary frameworks in order to create those kind of complicated but very reliable designs, standardized methods and regulations to be applied, and we need a lot of open source. Open source tools. I know that open source tools are just a few, and the reason is that they're quite expensive to maintain and they need capital. So most of the companies that are trying to, like OpenAI, that has actually started as an open source and became closed source company. But everything I've mentioned today and we've seen is within that sphere of machine learning and its subsets. We are not talking here about the natural intelligence, the AGIs and the ASIs, and that is another story. Okay. This is where the systems will learn from the real world, not the data that we give them, and they will be able to make decisions themselves. They will be able to store a lot of data and come up with new designs. And this is something that there is a lot of discussion out there, but believe me, most of it is still a lot of assumptions and like estimates that people are doing for the future. Again, another very good paper that I would like to, I highly recommend for people to read is the one from Gartner and the Impact Radar for 2024, where the different colors here are for different types of years. So now we are working on generative AI and knowledge graphs, a lot of researchers out there. This is what the new tools are coming up with, they are focusing on. In the next 1 to 3 years will be multimodal UIs, digital twins, and the things that I've mentioned that are quite important for our sector because of the complexity that our sector has. Subsequently, there will be a lot of research on behavioral analytics and self-supervised. The ones I'm circling are mainly for our sector, what we need there. And after that, we will see a lot of work on quantum processors, Web3, self-supervised learning, and spatial computing. Especially spatial computing, I think, will change a lot in the way we do things nowadays because it will manage to create models through pictures. Right, so 3D stuff through just a typical picture because it will use exactly our system, how we see the world, and we see the world in a 2D through our eyes. We don't see 3D. So in order to be able to meet the net zero emissions by 2050, you know that this graph, I'm sure you've seen it, where if we want to limit the global warming to 1.5 degrees by 2050, we will need to engage with those kind of tools. We need to be aware and try to understand them and work with them. So, closing the presentation, I think that as AI has been used by the medical sector for curing cancer and creating other drugs, we should be using AI for solving the sustainability issue and the CO2 emissions issue. So try to have that in your mind. And I would like to conclude the presentation with just a few words from late Steve Jobs in 1985.
My hope is that in our lifetimes, we can make a tool of a new kind, of an interactive kind. And so my hope is someday, when the next Aristotle is alive, we can capture the underlying worldview of that Aristotle in a computer. And someday, some student will be able to not only read the words Aristotle wrote, but ask Aristotle a question and get an answer. And that's what I hope that we can do.
Thank you very much. This is our website.